Hey, welcome back to your favorite trigonometry class. We're going to talk about simple harmonic motion today. We're going to build a model for an object in simple harmonic motion and analyze it. So simple harmonic motion, we got a special kind of vibrational motion which the acceleration of the object is directly proportional to the negative of its displacement from its rest position. Let me give you an example. It's usually easier to see it where we're taking in this figure, we have a figure B at rest here. Okay, that's at the equilibrium position. And what we're going to do is we're going to think about if we were to pull that down, right? We have this object and we stretch it out and then we let it go. If we let it go, then it's going to shoot up, then it's going to shoot down, then it's going to shoot up, anyways, until it finally comes to rest, right? So the amplitude is just the distance from the object's rest position to its point of greatest displacement. The period is just how long does it take to complete one vibration. For example, if we have it stretched out and then we let go, how long does it take? And we're ignoring friction, by the way, for it to get back there. Right? That's how the time it takes. That's one period. Okay, so it might be a little easier to look at this with a graph. So if we were to graph this, again, we've got this thing, we've pulled it down, right? We're sort of part here at C. Again, this is the resting position, but we're right here. We stretched it out, and we let it go. So we're starting down here a few inches away. We let it go, and let's say, I don't know, about a half a second later, it shoots up to position A, right? So it shoots up. And then another half a second later, it shoots right back down again. We're ignoring friction here. No frictional forces present. Okay, so there's no dampening effect going on. And this is a model of a simple harmonic motion. You see the trig function here, right? If you were to model that with time t as your input and displacement d as your output there. So for simple harmonic motion, let me give you an alternate way to think about this, or an alternate look at a simple harmonic motion. We're going to take a Cartesian coordinate system, and if we place an object at A0, you notice right here on the diagram, and if we move this thing counterclockwise, so we're moving it counterclockwise, let's say it goes to point P here, but we're going to continually moving this thing around the circle in a counterclockwise direction at a constant angular speed. So if we do this at a constant angular speed, we know angular speed, the omega, is theta over time. In other words, if I was to solve for theta, theta equals omega t. We're going to use that here in a second. Okay, so this thing's moving at a constant angular speed. Secondly, corresponding to this point P, wherever it's at after time t, right? So I've moved, and let's say after half a second, it's right here at point P. I have a point Q that's projected onto the x-axis. You see point Q right here, right? If I kept going around and point P was right here, now my Q projected onto the x-axis is right here. If I was to keep going right here, now that point Q is right there, and so on. If I go all the way around, let's see, right here, now my point Q is right there. I wish I could make two marks at the same time on my screen, but I cannot. But there's a projection, and so what's happening is this point Q is going back and forth on this x-axis as this is revolving around, right? Because I'm projecting it onto the x-axis, right? This point P projected onto the x-axis. So as I move around, that point on the x-axis is just moving back and forth on that x-axis. Okay. So that motion is a simple harmonic motion. It's a simple harmonic motion. So what we can do here is we can think about this. Let me erase this for just a second. If I go back to this, if I look at this cosine of theta, all right, we've got this theta right here, which is the adjacent side. Well, what's the adjacent side? That's our x over the hypotenuse. What's that distance? A, right? Now we know that theta, by substitution, if we replace theta, we know that's equivalent to omega t, because this is going around this circle in a counterclockwise constant angular speed. So what we have here, if I multiply both sides by a, we have a simple harmonic motion here. Okay, and we could make a we could graph this, right? This movement, if you will, as well, similar to that situation with the spring or whatever on the first one. So simple harmonic motion is going to follow one of these two forms, either with a cosine model or a sine model. So an object that moves on a coordinate axis, so that's displacement from its rest position time t is given by either of these. Okay, where a and omega are constants. The motion has amplitude, right? Remember, this is our amplitude, absolute value of a here. And then our period. Okay, so our period, so how long it takes, for example, if we stretched out that string, let it go, how long would it take to get back? That's our period, right? Because we have time, how long does it take? Right, that's our period. How long does it take? Well, the period is 2 pi over omega, right? Whatever omega is. Okay, so time required for one oscillation is your period. Time required for one oscillation. So when you're thinking about simple harmonic motion, just know that your period, capital T, this is in seconds, right? Because our time's in seconds here, per oscillation. Seconds per oscillation. Whereas our frequency is the number of oscillations per unit time. Okay, so this is the reciprocal of the period. So oscillations per unit of time. So per second. I'll just write per second. We're always in seconds. Oscillations per second. How many oscillations is it doing per second? Okay, that's our frequency. So again, reciprocal of the period, okay? Let's do an example here. Suppose an object attached to a coil spring is pulled down to a distance of 5 inches, right? So we've got this thing. It's right here. I'm gonna graph the time with its displacement. Okay, so we're starting right here, right? You see it stretched out, okay? And then we release it. So it's gonna shoot up, right? And it's gonna shoot back down. Again, we're ignoring friction here. So if we were to graph this, I'd graph this very good. Oh, that's awful. But anyways, we've got a graph, right? And we complete one period, right? And how long does it take it? Well, if the time for one oscillation is 3 seconds, if the time required for one oscillation is 3 seconds, so they just gave us the period, develop a model that relates the displacement d from its rest position after time t in seconds. Again, assume no friction. Okay. Now, so we're stretched out down here. We'll say this is looks like it's at 5 inches from its resting position, so -5. I'm going to use the cosine function. So I'm going back here and I'm like, which one do I want to use? Do I want to use cosine or sine? Well, this is looking like a cosine graph. A sine would be, a sine situation would be like if you have an object at its resting position and then it's moving down, right? That'd be more like a sine situation. So I'm going to use a cosine. D of t equals a cosine omega t. So d of t equals a cosine omega t. Okay. And number one, they said at its resting position, it's 5 inches. So d of 0, you know what, I got to get rid of some of this here. So d of 0, hold on here, d of 0 times 0 is 5 inches, so it's down at -5. Remember we had this graph, right? T, d of t. Now cosine of 0 we know is 1, so our a, we just solve for our a. Our a is -5, so there's number 1, step number 1. Let's go ahead and find your a if they tell us our initial position, right? At time 0, we can solve for a. Now the other thing that we need a number here for a. We also need to know our omega, but they gave us more information. They said if the time for one oscillation is 3 seconds, so it took them 3 seconds to do one oscillation, right? They just gave us the period. So number 2, the period is 2 pi over omega, and they said that's 3 seconds. So if I solve for omega, it's 2 pi thirds. Now can we develop the model? You bet we can, because now we know we have a and we have omega. So d of t equals a cosine omega t. Throw in our a, throw in our omega, and we've got our model. And if you were to graph that, you'd see that cosine function. Again, we're assuming no friction with this. There's a little bit of work there as well. All right, second example here. Suppose the displacement of an object is given by this function, so we're given a model here. Describe the motion of the object. Well, if it follows d of t equals a cosine omega t form, or d of t equals a sine omega t models, either of those two models, we know the motion of the object is simple harmonic motion. Okay. B, what is the maximum displacement from its rest position? So part B, I say, well, that's my amplitude. It's the absolute value of A. All right, so it's the absolute value. Remember, this is in this form, A sine omega t. So the A is at 6. So it's the absolute value of 6, which is 6. Maximum displacement of this from its rest position will be 6. So it goes high as 6, as low as 6. What's the time required for one oscillation? Well, that's our period. We're wanting to know how many. Remember, the period is in seconds per oscillation, right? We want to know the time required for one oscillation. We want to know the period. So part C, what's the period, time required for one oscillation? We say, well, period is 2 pi over omega. What's omega? Omega is the 2 right there. Sine 2t is 2. So we got 2 pi over 2. So our period is pi. And this is in, remember, this is in seconds per oscillation. So this is seconds. It takes pi seconds per oscillation. In other words, 3.14 seconds to complete an oscillation. Part D, what's the frequency? Well, the frequency, if you remember, is the reciprocal of the period. In other words, it's omega over 2 pi. So I just flips that period around. Instead of 2 pi over omega, it's omega over 2 pi. And remember, our omega is that 2 right there. So we got 2 over 2 pi. So we got 1 over pi. That's our frequency. And our frequency is in oscillations per second. So 1 over pi oscillations per second, that's like, I don't know, 0.32 or so, somewhere in there, oscillations per second. Right? It's 0.32 oscillations for every second. Right? That's what it's saying. That's what our frequency is informing us about. Well, that's it for our simple harmonic motion. I appreciate you listening. We'll see you guys next time.